Hello, this is the next video in a playlist that I'm calling General Linear Models, Design of Experiments. And this is part 2 of a little mini series within that playlist that I'm calling Randomized Complete Block ANOVA. And here we're going to look at the perpendicular projection matrices and column spaces associated with the design matrix. Now, in this video, I decided how much do I want to reprove, how much do I want to point back where the proof is in another video, and I decided to do the latter, that I'm going to make statements, and if you want to see the proof, then you will see another video. But I really seriously debated on that. And so we're going to see videos in a little mini series that I'm calling Repeated Measures, One-Way Fixed Effects ANOVA. And there's 2 videos, perpendicular projection matrices, what I'm going to call BV1, background video 1, and the column space of the design matrix, which I'm going to call BV2, background video 2. Now the model, as a reminder, is y equals x beta plus epsilon. And now initially I didn't have the star, but I added it because I don't want this beta confused with this beta. So the epsilons are IAD normal, mean vector 0, sigma squared I. See part 1 of this little mini series where we partitioned it into these two. This is the design matrix and this is the vector of parameters, mu, tau, and beta. Now, to find the perpendicular projection matrix onto X, we broke it up into pieces and then used that to find the overall structure of the perpendicular projection matrix on the X. So what we did was, so PPM stands for perpendicular projection matrices. So let's let MJ, M tau, M beta represent the perpendicular projection matrix onto the column space of X, column space of 1, column space of tau, which is associated with the treatment, column space of beta, x beta, which is associated with the blocks. And see background video 1 for much more detail, proofs, etc. Now M, to be a perpendicular projection, the way you construct it is X transpose X, generalized inverse X transpose. Now this, we have to use a generalized inverse because this is not a full rank matrix. The column space in ANOVAs are not full column rank. So when we create this matrix, X transpose X, you can't take the inverse of it. So it's a generalized inverse. So J is the perpendicular projection matrix onto the column space of 1, so a 1 vector. And that's 1 transpose 1 inverse, 1 transpose. And this is a 1-by-1 matrix of AB. So when you take the inverse, you get 1 over AB. And then these two matrices create a matrix of all ones, which we call UAB. So if there's a number here, that tells me how many columns this matrix of all ones has. And then this is how many rows. But if the columns are left off, then we assume it's a square matrix. So this is a square matrix of all ones, AB by AB, and then times 1 over AB. The perpendicular projection matrix on the column space of X tau is this X tau transpose X tau inverse, X tau transpose, and it's a block diagonal of 1 over B U. Block diagonal means all the off diagonals are 0, but down the diagonal is this matrix here. It's a matrix of size B by B, and it has 1 over B of all the elements. Now the perpendicular projection matrix on the column space of X beta is M beta, and it has the same form, X beta transpose X beta inverse, X beta transpose. And it's block diagonal 1 over A I. Not block diagonal, block. Block means that the whole, if the matrix, you go by row putting this in it, then you go to the next group and then put it in it, and then so you go block by block putting this in it. And see this BV1 for more detail on the structures of these. Now the properties of the mean vectors is the transpose of J is 1. And to me that makes sense. You know, J is a matrix of this form. So if we add up AB1s, remember this is a matrix of all ones, we get AB, but then when you divide by AB you get 1. It's symmetric, it's idempotent. When you pre-multiply the y vector by it, you get the grand mean vector, which is a constant vector of all, you know, the same quantity, of which is the grand mean, y dot dot bar. X, yeah, the trace of m tau is A. M tau is symmetric, it's idempotent. I mean, and that pretty much has to be because it's a perpendicular projection matrix. When you pre-multiply y by m tau, you get what we call the treatment mean vector, and understand its structure. So the first B components of this vector is the grand mean, or not, it's the treatment 1 mean. The next B is treatment 2 mean, all the way to the last B elements of this is the treatment mean for group A. So the trace of m beta is B, and since it's a perpendicular projection matrix, it's symmetric, it's idempotent, and the block mean vector has this structure. Now normally, you know, I think of it as a column vector, but to save real estate, I transposed it. So block 1 mean, block 2 mean, all the way to block B mean, and then that repeats A times. And that's the structure of the block mean vector. Now the properties, column space, and perpendicular projection matrices are this. Note that the column space of 1 is a subset of the column space of tau. And you can see that if you add each of these columns of x tau, you get the 1 vector. So this is a subset of that. Same way for x beta. The column space of the 1 vector is a subset of the column space of x beta. Now, all these multiplications equal j, m tau j, j m tau, m beta j, j beta, m beta, m tau m beta, and then m beta m tau, all equal j. And this is proved in the background videos. Now, these matrices are perpendicular to each other, or orthogonal. That means the product of these, the pairwise product, are all 0. And again, this is proven in the background videos. Theorem 1 in BV2, background video 2, the m tau j projects onto the column space of x, but orthogonal to the 1 vector. In the same way here, m beta j projects onto the orthogonal complement space of 1 vector, but with respect to the column space of beta. And what this means is, let's just look at this one here for a second. If we pre-multiply a vector, so some vector dangling in AB space by this, it shoves it into the column space of x beta, but orthogonal to the 1 vector. So that's what this means. See theorems 4 and 5 in BV2, that this column space is the same as this column space, which is the same as this column space, which is the column space of x. And the reason that becomes important, and I'm going to point you to theorem 2 in BV2, is that this ends up being the perpendicular projection matrix on the column space of x. Now, you know, if you do this addition and subtraction, you end up with this. But we also know this is how you create a perpendicular projection matrix. X transpose X generalized inverse X transpose. We know for fact that that's the perpendicular projection matrix on the column space of X. But since perpendicular projection matrices are unique, and I must say, see property 4 in a video that I titled Perpendicular Projection Matrices, those two have to equal. And now we know the structure of the perpendicular projection matrix on a column space of X. By theorem 7 in BV2, we know the rank of M is A plus B minus 1. And that's going to be important when we develop tests for this in this setting. Okay, well that's all I have for this video. The next one we're going to look at sums of squares and F-tests in the randomized complete block design. So I hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks, bye.